All right, question number 16. So we have another cluster starting here. Tells us that we are going to use answer questions 16 through 20. So that means that any of these diagrams or tables are fair game for questions 16 through 20. Okay, so if you need to flip back, you can. So they gave us some background information about stars in the Big Bang. So it says our sun is a 4.6 billion year old yellow dwarf star. It was formed either from matter produced during the Big Bang or from matter released when large stars reached supernova and exploded. This matter, in the form of hydrogen, contracted into a denser gas cloud due to gravity. The temperature at the cloud's core increased, allowing for the fusion of two hydrogen nuclei into one helium nucleus. The mass of this helium nucleus is slightly less than the mass of the hydrogen nuclei. This difference in mass is the source of the star's energy. The model below shows some information about the life cycles of different stars. Okay, so we have a model showing, remember, life cycle is the stages that it will go through over time. And we are split into three different categories. So we have high mass stars, medium mass stars, and low mass stars. And you can see that they kind of all start in the same place, so a gas and dust cloud, but they progress through different stages and ultimately end as something different depending on how they started. Okay, so our first question says identify the factor that determines the lifespan of the sun and other stars. And we have just one line, so it's looking for just a simple one or two word answer here when you have one line, and it says to identify. Okay, so if I look, the lifespan of this star becoming a supernova black hole neutron star versus this star becoming a red giant, a planetary nebula, and a white dwarf is the fact that this was high mass and this was medium mass. So our answer here, how they are different, is their mass, or you could have said size. Okay, but it says high mass, medium mass, and low mass. So we're looking for mass here in terms of how these stars are different. All right, question 17 introduces a new table. It says the table below shows some information about different types of stars. Solar mass is the mass of the star compared to the sun. So that's this column here. So 10.3 means that this star is 10.3 times the mass of the sun. We have distance from the sun, so how far away it is, and we have the approximate lifespan, which is just how long it will burn for and produce energy. And our question says, a student created a data table containing information on how stars synthesize common elements through nucleosynthesis. Okay, so we're talking about the process of nucleosynthesis. Which row of data correctly identifies all of the characteristics for that star? Okay, so we need to know which of these is true. So when I look here, I see that we have nucleosynthesis, which our table did not tell us anything about, but we have mass and we have lifespan. Okay, so I'm going to pick one of those columns and I'm going to see if they match based on my title up here that was given to me. So approximate lifespan was given to me and solar mass was also given to me. And I'm going to eliminate. Okay, so I'm going to start with row 1. So my star is the sun and I'm going to use lifespan. And so my sun here has a lifespan of 9 billion years, but my table says it has 4.6 billion. So that does not match. So I'm going to get rid of row 1. So that is not going to be my correct answer because that lifespan does not match. I'm just going to keep working my way through. So I have Sirius B 0.23, Sirius B 0.23. That's good. That matches. And then I have Aldebaran 6.4. That matches. And Wolf 359, 4.1, that matches. So those are good. Okay, so lifespan at least helped me get rid of one of those questions. And then I have high mass versus medium mass left over. So my mass was given to me as a value. So the first thing I want to look at is kind of how my values, what is my range? So I have 0.09, super, super small. I have 16.5, 10.3, those are quite large. And then I kind of have these in the middle that are right around 1. So if I was to split this, I would say that these are my high mass. They're the biggest. Wolf is definitely my low mass. And then right around 1, those are going to be my mid or my medium. Okay, so I'm going to match my stars for mass here and see what we think. So I am going to look, Sirius B is 0.98. So I considered that mid. So I don't think that that makes a whole lot of sense there for high mass. So we can get rid of that one. And we're going to get rid of 2. And then we have Aldebaran, which is 1.16, which we did consider medium mass. And then we have Wolf 359, which we considered a low mass. Okay, so that leaves us with option 3. And the last thing I have to check is nucleosynthesis. So nucleosynthesis is going to be, we have a reference page, page 2. So generalized nucleosynthesis. And if we look, Aldebaran says a helium changes directly to carbon. And if we look here, helium changes to carbon. That is correct. And so that works out there. We can check that one off. And we are left with option number 3 being our correct answer. Okay, so actually Wolf 359 we could have gotten rid of based on nucleosynthesis as well. So if we look, it says hydrogen into carbon, but here it tells us hydrogen actually turns into helium. So hydrogen into carbon would not work. So that makes that incorrect. And that could have also been used to get rid of Wolf 359. So in this question, we didn't necessarily have to know anything. We just had to know how to use the data that was given to us to eliminate answers that did not make sense. All right, question 18 gave us a new reading and introduces a new graph. So it says sunspots are areas where the magnetic field is about 2,500 times stronger than Earth's magnetic field. Because of this strong magnetic field, the magnetic pressure increases and the sun's surrounding atmospheric pressure decreases. This lowers the temperature relative to surrounding areas because it inhibits the flow of new super hot gas to the surface. Okay, so we're starting by talking about kind of what a sunspot is. It says that the pressure increases, the atmospheric pressure decreases. So we have an increase in magnetic pressure, a decrease in atmospheric pressure, and a lower temperature. Okay, so those are kind of the information that is important there in terms of this first paragraph. Sunspots occur in pairs because they have magnetic fields pointing in opposite directions. However, from 1645 to 1715, there was nearly zero sunspot activity. Okay, so that's important. This time period is referred to as the Maunder minimum. So minimum means low. Some scientists also call this time period on Earth the Little Ice Age. Okay, so that is ice age is when it's super cold. So what I'm seeing here is that when there was no sunspot activity, we had very cool temperatures. Okay, so that's kind of showing me a correlation there between temperature and sunspot activity. So I'm actually going to write a little note here. So I'm going to say no sunspots or decrease in sunspots equaled decrease in temperature. Okay, that's what we're seeing based on this statement here. All right, then we have a graph. Remember these graphs, when we have these pits and peaks, these are called cyclic. So they're happening over and over and over again. And we can see that by the rise and fall of that line. So our question said, using the information from the passage and the graph, place a check mark in 3 boxes to identify the statements that accurately describe sunspots. So 3 boxes, that was important. So a lot of people miss points on these questions because they did not carefully read and they did not choose 3 boxes. They chose more than 3 or less than 3, and that automatically caused them to miss this question. Okay, so our first one says a decrease in the number of sunspots is inferred to decrease Earth's temperatures. Okay, and we actually wrote that up here. So we read in here that 0 sunspots caused a ice age. So no sunspots cause low temperatures. So that is going to be correct. So we're going to check that one off. Okay, so we need 3 total, so we need 2 more. So the next one says the number of sunspots changes each year in occurring in approximately 11-year cycles. So a cycle means I need to go from peak to peak. I need to figure out how long it takes to go from a peak of the graph to another peak of the graph. Okay, so I'm going to look here and I'm going to find my peak. Right there. So if I look, that's 1955, 56, 57, 58. So 1958, I had a peak here. And then my next peak is here. And that is in 65, 66, 67, 68, 69. And so I could either figure out using my calculator how many years were between 1958 and 1969, or I could simply count, right? So if I start here and I say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that was an 11-year difference. Okay, so I have 11-year cycle there. That's what that's showing me. And if I was to continue, I could check another one and I would see the same thing. So this is showing me that this is true. It happens every 11 years as a cycle. Okay, my next one says an increase in solar output is associated with a decrease in the number of sunspots. Okay, so an increase in solar output is associated with a decrease in the number of sunspots. So what I found is that for a lot of my students, it was difficult to kind of tell if this one was true or not. So something that we did is we said, okay, if I wasn't sure, so maybe I read this one and I'm not really sure if it's true or not. I know that I need 3 total check boxes, and so far I have 2, so I have 1 left. So I'm going to skip this answer for right now, and I'm going to read the next one. I'm going to see if maybe one of these 2 makes sense to me, and that would eliminate that third one anyways. Okay, so the next one says the average number of sunspots appearing each year has decreased steadily since 1950. So decrease steadily means I only see a decrease over time. So 1950, and if I look, I actually see a decrease here, but I see these little increases, and then I see these overall increases as well. So we definitely do not have a steady decrease here, and so that makes this one incorrect. And I'm going to read my last one. Sunspots are regions of cooler temperatures on the surface of the sun. I'm going to go back to my reading here, and we underlined that this lowers the temperature relative to surrounding areas. And so that is true, right? So when I have sunspots, they're on the surface of the sun, and they are going to lower the temperature. And so that is going to be true. We want that last one. So that means that this one was incorrect. Okay, so even if I wasn't sure how to prove that one is incorrect, by skipping it, we were able to eliminate it because we knew that this one was true. Okay, and now we're introducing another reading and graph for question 19. So 19 says, in the 1920s, Edwin Hubble studied the motion of galaxies. He found a relationship between a galaxy's velocity as measured from Earth, which is called the recessional velocity, and the galaxy's distance from Earth. This relationship is known as Hubble's law. This law has implications for understanding how the universe has changed since the Big Bang. The graph below shows data on several galaxies' distances from Earth in megaparsecs and their recessional velocities. Okay, so the first thing I always look for on a graph is the title. So we have a relationship between distance and recessional velocity. Down here at the bottom, my scale is distance to the galaxy, and then over here we see recessional velocity in kilometers per second. Okay, and I see that I have all these little dots, and then I have this best fit line that comes through, showing me that all those measurements are staying right around this general slope in terms of our data. Okay. So question 19 says the relationship between galaxies' distance from Earth and recessional velocity graph shows that the recessional velocity of a galaxy blank as the galaxy's distance from Earth increases. So I have these lines with letters, and it looks like it's asking me to kind of complete the paragraph using the words that are given to me in each table. Okay. So if I look here, I'm going to look at for my differences. So I have A, increases proportionally. Those are the same. And then I have increases non-proportionally for my other 2. So we know that it's increasing overall. So the difference here is proportionally means that I have a constant slope, and my data points are pretty close to that constant slope. Okay, so that tells me here that I have this constant line and I have my data points very close. So if I was non-proportional, I might see something that my line looks more like my slope is changing over time, where my slope is not staying consistent, and we do not see that on this graph. Okay, so that would be proportional because the slope stays the same. So we're going to get rid of A for 4 and A for 2. So we know that 4 is not correct, and we know that 2 is not correct. B is the same for each of them, expansion. So our difference is going to be, should C be filled in with compacted, or should it be filled in with inflated? Okay, so I'm going to keep going. So we decided that the recessional velocity of a galaxy increases proportionally as the galaxy's distance from Earth increases. This is evidence for the expansion of the universe and suggests the universe initially was blank at the time of the Big Bang. Okay, so if we think about this, we already identified that our universe is expanding. So I need to think about compacted. So it's saying it was initially, so in the beginning of time. So if I'm going to be expanding, was I initially together as a single point and over time I got more separated, or was I initially inflated, so spread apart, and over time I came together? Okay. And so the Big Bang suggests that we started as a single point and over time we spread out. So for C, our best answer is going to be compacted, which leaves us with number 1 as our best option. All right, number 20. So they've introduced another graph and reading for us. It says particles were created as a result of the Big Bang. The first particles were subatomic particles like the protons, neutrons, and nuclei of later elements such as hydrogen, helium, lithium, and beryllium. The graph below shows some information about these particles, the temperature of the universe at the time they were created, and the amount of time after the Big Bang that they were created. Okay, so we have lots of information on this graph. So we have a scale up here at the top, which is time. We have the relative amount of particles, and we have temperature on the bottom. And then we have a bunch of different lines, and they're labeled for which elements they are representing. Okay, so what we're going to do is read our question, and then we're going to think about how this graph might help us. So it says, based on the information from the relationship between relative amounts of different particles and temperature of the universe after the Big Bang over time graph. So they're telling us that we need this graph here. Which table correctly identifies the composition of matter in the universe as evidence for the Big Bang theory? Okay, so we have the unit of time. We have what kind of particles were present and what was happening to them, and then we have temperature. So we have to check that all 3 of those things are true as we are looking at this graph. Okay. So first thing says our time range is from 10 to 100 seconds. So I'm going to use different colors for each one so we can kind of see what we're looking. So from 10 to 100, if we look at time, that is 10 to 100 here. So I'm looking at what happened in this time period. And it tells me that I had hydrogen and helium decreasing. So I'm going to go over hydrogen with my blue pen so we can look at that line. Okay, and so if I look, hydrogen, so this tells me hydrogen and helium were decreasing, but if I look, I see that this line is increasing. Okay, so that tells me that that is not correct. We did not decrease. So I'm going to get rid of option 1 because that is not true. Okay, our second option says from 100 to 1,000 seconds. So if I look up here, 100 to 1,000, it's going to be in this region here, this yellow region. And it says that hydrogen increased, then decreased. Okay, so I'm going to check that first. Hydrogen increased, then decreased. So here's my blue line of hydrogen. Hydrogen increased, then decreased. That is true. Okay, so I'm going to check that off. That's accurate. And my next one says helium, He, increased, then remained constant. Okay, so I'm going to highlight that in pink. So He, so helium. So I have helium-4, which appears to be this line here. And I have helium-3, which is this line here. So I'm going to check that they both do the same thing that this stated here. So helium increased and then remained constant. So here's my yellow. So I see helium increasing, and then constant means it kind of stays flat. So I see it flat there. If I check my other one in my yellow area here, it's increasing. There it's remaining flat. That is accurate. We are going to check that off. That looks good. That looks like so far it's working out, and I just have to check my temperature. Okay, so it's telling my temperature decreased over that time period. So temperature is on the bottom here. So if I look in my yellow section, my temperature started here and it ended about here. So it moved from just before 1 times 10 to the 9, it moved towards 3 times 10 to the 8. Okay, so in this case, we have to be careful. We can't just use the 1 and the 3. We have to look at the exponents first. So this one says 10 to the 9, and this says 10 to the 8. So since my exponent is decreasing, that means that this is getting smaller. So my temperature is also decreasing. So that is true. That looks good. So my correct answer is number 2.